Okay. Invited Mark. And I think there's Mark Feely, I believe, is here. Okay,
Can
also
you hear me?
invite. Yes, invite Mark. Also, the other invite Mark Feely up also.
I just invited him. Okay. Oops, I invited Michael, the wrong guy. Excuse me, Mike. I'm going to cancel that.
Okay.
He's on. Mark Feely's on stage. So, do you want to start 5 minutes early or start right on time?
I think it'd be good to start on time, probably.
Sure.
Yeah. So we've got. Shall we take a break and resume in 5 minutes?
Sure. That's long enough for people to take a bathroom break or get a drink or something like that. And this talk, I believe, is a lightning talk and won't be the full time. Is that right? And so we'll have a little break after this talk as well for people to go and have maybe a little discussion in the lobby. Okay, but yeah, this will be a short break. It's only going to be about 3 minutes. So if you need to get a drink or whatever, feel free.
I propose that we not even do a take a.
I don't think we have to do an official break. We just go ahead and get
very good.
ready.
We'll just,
but after this will be a real break until the next lightning talk, and then we'll have a real break after that until the next session.
I'm going to fill up my glass of water and make sure I don't spill it.
Okay,
do not spill on laptop.
Yeah, do not spill your glass of water. That'd be bad.
Be right back.
All right, we'll see everyone in a few minutes.
Okay. Okay. Break time's over. I hope you got a drink or a snack. Now for the next talk in our session. I'm hearing some feedback, but I'll go away in a minute. Okay, so this next lightning talk will be by Marc-André Belanger. Am I pronouncing that correctly?
Belanger.
Belanger. And Mark Feely. And I think Mark Feely is well known in this community for work on Gambit Scheme for a very long time. I even have a couple of Gambit Scheme t-shirts that I wear. Okay, so we're going to be learning about a lightweight approach to accessing Python modules from Gambit Scheme. And this is interesting and important because, as Jeff was talking about and invited to talk, Python really has become extremely important language in machine learning and many other areas. And I see this in my own work, that not having access to Python libraries can mean sometimes that you can't really use Scheme. So having better way to interoperate with Python, I think, is important for modern software development. All right, take it away, Marc-André.
So thank you for the introduction. And like you mentioned, the motivation for this work was actually I needed to use some Python libraries that I wanted to use from Scheme, and that's where we went. So this work is actually an extension of what we presented at ELS back in May, where we presented actually JavaScript FFI, JavaScript to Scheme FFI, which I encourage you to look at this paper for more details, because this is a lightning talk, and I won't go over all of the implementation details. So what we're going to see today is a work in progress integration of CPython 3.5 and over. So that's what we tested it on, and Gambit Scheme. We made it work on Linux, macOS, and Windows. And the most interesting thing that I'm going to show to you is actually bidirectional interface from Scheme to Python and Python to Scheme, but with a focus on a high-level interface, which is based on Gambit's own 6 infix syntax extensions, which is based on a reader extension. The actual integration is very low level, so we have to, as you can imagine, we have to make a lot of tight couplings between Gambit and CPython. And this requires to build the CPython development sources we have a sensible amount of introspection to make sure that we can build the cross-platform and get the right information for linking and everything. This is done by the Python interpreter. And in order to manage the access to the Python package index, we use a separate virtual environment for Gambit. So for those of you who don't know what that is, it's just a standard way in Python to manage packages that you install in order to separate them from packages you want to install in other projects, for example. So in this case, Gambit has its own virtual environment and doesn't use the system one. What we're going to see in this short talk is some code examples of how it works. And so we have first we'll go over a basic example of pure Python, and then show how to access the Python package index, which has a collection of over 300,000 Python packages. Of course, we haven't tried them all, but you can actually interface directly to pip, which is a package installer, and download and install any package that you can compile on your system. And if time permits, and if you have any questions, I have a few other examples that we can show. So let's go and see the simple example. So the simple example, let's just start by importing Python. This is actually a package that repackages sub-packages, and what each package does should be described in further publications. So now that we have Python, we actually have access to what we call the low-level interface. And so Python has a C API, which we can access through the Gambit C FFI. And as you can see here from the code here, it's not very practical if you want to write Python code. You have to evaluate in the case of expressions, and you have to exec in the case of statements. But it's practical if you need to execute a lot of code that you can, for example, copy-paste from online. So what you see here on this line is actually just the Gambit Scheme representation of the foreign Py object. Now, what's most interesting in our approach, we believe, is this. So the high-level syntactic interface is what we introduced in the last paper and what we use here. So what it allows us to do is use an infix syntax directly in Scheme code. Let's say I want to invoke Python. So what you see here is it's analogous to quasi-quoting and escaping in Scheme, so in macros. So for example, here I want to jump into I tell the reader I want to jump into the infix syntax, and then I can write infix. And so 5 times 2, this is transformed into an expression, Python expression, sent to the Python interpreted, and the result is sent back and converted automatically. Now, how do I know that I'm really in Python? Well, I can just do this, which actually shows that this is the proper Python behavior. You wouldn't get the same if you would do that in Scheme, of course. And in this infix extension, we want to be able to insert at will Scheme expressions and mix and match Scheme and infix expressions. So I can do something like the backtick, and then the Scheme expression that I write will be evaluated, converted, and then passed back to the Python interpreter. And we can see this works. So I can evaluate a bunch of other expressions, and we can go through them one by one. So this is simple. The grammar for our reader is not the grammar for Python, but it's pretty similar because we want to target multiple languages. Ideally, we target C. We want to target a part of Python and a part of JavaScript, so we have to have a sort of hybrid grammar. But we can understand things such as arrays, lists in Python. And here you can see that we can also make assignments. So let's say I define a L equals 1, 2, 3. So this is a list. I can assign items directly through invoking it from Scheme, sending the results to the Python interpreter, and evaluating this. So what you see here is actually the syntax, the 6 syntax. But what does it look like when we evaluate it? What do we emit to the Python interpreter? Let's just, I have to import 6 expand. So this will allow me to toggle the debug mode for 6. Then if I put in an expression here, what you can see is exactly what we are emitting to the Python interpreter to be evaluated. In this case, we call we just have a function counter. We define a function. It's called gfunction17 in this case, because it's the 17th or the 18th expression. And what we do is we evaluate this, and we get the result back. In the case of an expression, a Scheme expression, you can see the difference here is that this function accepts an argument. In this case, it's the ____1 argument. What this argument is the scheme expression that will be evaluated in the interpreter, then passed, converted and passed to the function, the Python function, evaluated in the Python interpreter, sent back to scheme. But we don't want to see all the output emitted. Now, I told you there were some automatic and bidirectional conversions. We're not going to go over all of them, and most of them will be similar to what was proposed in our previous JavaScript FFI. But as you can see, we have some convenient ones. For example, the table, a scheme table will be converted to a dictionary, and we chose that a U8 vector will be transformed to bytes. Maybe more importantly, when you see here the procedure, so a scheme procedure, we have to figure out a way to implement this in the Python side. What we chose to do was play a little bit with classes and what Python, the CPython API calls capsules, in order to pass around pointers to the proper scheme objects, such that we can invoke the correct function from what is basically just a stub called a scheme procedure, which creates a C function using the CTypes API. And we could go over the details of this if you're interested later. Basically, we do the same thing for a scheme object. So when we want to pass a foreign object to the Python interpreter without touching it, in this case, we call these pass-throughs. We have to put the pointer to this object inside what we call a scheme object class. So this is just low-level mechanics of how to pass around things. But the most interesting part is the actual working syntax, which we call 6. So if you want to pass around untouched objects, you can pass scheme objects to JavaScript in this way. Let's say we define f to be a foreign. What does it mean to be a foreign? This is a foreign which is invoked in Python runtime. Well, a foreign is an object that, if we hadn't called foreign, would have been converted by our system. In this case, it's not. And so it's a direct pointer to the Python object. What this allows us to do is, for example, we can make what we call manual conversions. So for the moment, manual conversions are a little bit clunky. They're not integrated directly into the automatic conversions. That's something we want to work on later. But if I convert the list to a vector, as I've done here, you can see that contrary to the ordinary conversion, this one was not recursive, and so the items of the list haven't been converted, and I've converted it to a vector instead of a list. Now, how do we work with module imports? Because that's what you want to do in Python. Well, you just import them. So this works with all imports that you have available. The /import syntax doesn't work with all of the Python import syntax, because that would be a little bit more involved to implement inside the reader extension, and that's not necessarily something we want to explore. So these are just examples to see that the extensions work. The area calculated in Scheme is equal to the area calculated in Python, and everything works. For this, we have, if you want to install Python package index, we just have simple shell commands that we invoke with these scheme procedures. Now let's see what happens if you want to invoke packages, but you've installed them from the package Python package index. In this case, this example, let's go over this example. We use the requests. It's a very well-known Python package. And this package allows us to make HTTP requests. In this particular case, I set up an account and an API key to the Open Weather Map. And the Open Weather Map allows me to get the weather in Montreal at this time. So what we've seen here is I've loaded my API keys and defined the URL that's just based on the REST API. And here, I invoke the requests.get method, pass it the scheme evaluation that creates the proper string. And then on that object, I invoke the JSON method. That gives me back a dictionary, which is then automatically converted to a table. And then I can just use as I would any other table in Scheme. Now, let's see another example. What you see here, PyExec, I have to use it, as I mentioned, because the import, this syntax doesn't accept from something import foo. And so I import Flask, which is a web framework, which is very well known also in Python land. This is just standard setup. And what's interesting is that you can almost copy paste code from a tutorial or something. And I defined a handler. This handler, basically all it does is it gets the weather and then returns the string current temperature in Montreal with the temperature. Now I define a route, which is Flask's way of assigning handlers to paths. And I can serve it. So app.run will just launch a web server. And you can see that this works. Didn't work. So all right, so it's running on localhost 8080. And let's just see, make sure we get a response. And so the weather, current temperature in Montreal is 20.5 Celsius. Now, in conclusion, this is a work in progress. We have a lot of things that we want to work on. Notably, we want to work on proper integration of user-defined conversions. And so we want a mechanism to integrate these user-defined conversions to be automatically included in the automatic conversion. We have to make sure we test properly the global interpreter lock in Python. We have to test this. We have obviously to test for memory leaks. We have to implement what we want to implement is threading in order to not block the main scheme thread when we call Python. We want to investigate richer interaction with scheme foreigns from Python. So for example, in Python, you can see what the foreign structure of the Python object is in the scheme REPL. We want to investigate if we can do the same thing, but from the Python side. Then the cross-platform builds are kind of hard. We have a somewhat robust cross-platform build, but Windows is something we need to test more. And another interesting thing that we want to look at is automatic import of Python module exports. And so if a module exports a certain number of names, we want to be able to automatically import them when we import a Python module. So for this, I want to thank you for listening to my talk, and hopefully you have some questions.
Thank you very much, Marc-André and Mark. Do we have any questions? So, do issues arise from differences between object representations? For example, Python lists are not null terminated like scheme lists.
So obviously, Mark has done a lot of low-level work in order to make sure the conversions happen properly and successfully. From the Python side, it's not that hard because we have the Python C API. But when you have to make the conversions from Python to Scheme, yes, it's Mark did a lot of careful work on this, because you really have to know the deep internals of the object representations at the C level. Hopefully that was clear.
Let me mark that as answered.
Here we have a question from Olin Shivers. Can a user of the system install custom converters for specific kinds of objects?
So you can define them, but they're not. There's no mechanism at this moment that allows you to register them and have them automatically run when you invoke the 6 infix syntax. But that's something we want to do. So.
Do we have any other questions?
Do you want to see what a TensorFlow example looks like, which is I just took the TensorFlow tutorial and adapted it to our system.
Sure, you've got 9 minutes left if you want to show TensorFlow.
Yeah.
It's obviously that's exactly the sort of library that people want to use Python for.
I'm not going to run this, but can you see my my mouse?
Yes.
Yes.
Okay. So I'm not going to run this, but what you can see here is that anybody who knows Python, and in this case TensorFlow, should understand what's going on. That's what the infix syntax allows us to do. So it allows us to sort of bridge the mindset that you would have in Python and bring it back to Scheme. And of course, everything that we've shown, we're using the raw interface. Nothing stops you, and actually it would be better if you would develop a library that uses the 6 interface in order to write only Scheme code, almost only Scheme code. You could do that with our extensions.
So can you tell us what this example does?
This is so I don't know the TensorFlow library. What I was interested in is it's a very well-known library. Can I reproduce the example on the website? And so I just went to their website and I copy pasted this, and it works. So, with some small changes, what you can see here is that we have the high-level interface isn't able to parse properly every kind of strings that we pass it, and so in this case we have to drop back to the lower-level PyExec or PyEval interface. But the point of this was to try out. So can we just install any package and make it work? And it does.
I may have missed this. Does this work with Python 2 or Python 3 or both?
It's 3.5 and over. We haven't tested the whole combinations and permutations of 3.5 Windows, Mac OS, and Linux. On Linux, it's 3.5 and over. I think Windows, we tried 3.8. Mac OS 3.5 to 3.9. And the installation compilation is mostly, once you have Python installed, is mostly automatic.
Do we have any other? Thank you. Do you have any other questions?
Or maybe Mark wants to say something.
Mark?
I'm not sure what to add. So, I mean, as you say, it's a work in progress, and we'll keep working on this. But I think the main parts are there. The rest is mostly sugar on top of the basic implementation. I think the interesting part is that there's this high-level interface where conversions are done automatically. So you can write code that just works in a very natural way, but you do have this ability to share objects between Python and Scheme when you need to. When you need to have a pointer from Scheme to a Python object and you want to be able to mutate that object from Scheme, then you do have that ability. Otherwise, the high-level interface is basically one where objects get copied from one world to the other. So if you have a Python list, you get a copied list on the Scheme side when that gets transferred over, and similarly in the other way around. So I think it covers pretty much all the bases for being able to write high-level code, but also gives you the ability to control things at a lower level of abstraction if you need to share objects between the two worlds.
So I have a question. If no one else is going to go, I will jump in. Can you say a bit more, either one of you, about how you invoke scheme closures from Python? When you have to hand control back, how does that work?
You mean with the low-level global interpreter lock, or?
Yeah, when you're running along in Python. I mean, I assume that at the top level is Gambit Scheme. And then from Scheme, we call into Python, and we pass into Python a data structure, let's say a hash table that has a bunch of functions in it. Python is running along, it reaches into the hash table, pulls out a function, but it's a Scheme function. Now we're executing Python code. Python wants to jump over and invoke the closure, the Scheme closure. Do you use a trampoline? Do you suspend the Python, or do you directly, how does it work?
Let me answer that, because I think our time is limited. I think Marc-André explained the Scheme procedure type that you have on the Python side, which is a class that essentially contains a method that is the call method. So you can call instances of this class, and these instances also have inside of them a foreign pointer back to the closure that exists on the Scheme side. So when on the Python side an instance of Scheme procedure is called, then it invokes the machinery that makes the call on the Scheme side.
Okay.
Because you have this reference to the actual Scheme closure that is being held by the Scheme procedure instance.
If we have time, a last question, which is, what do you do about garbage collection?
Each system to his own?
Yeah, but what if I pass a Scheme function into Python? Python stashes it away in some Python collection, and then we return back to the Scheme code. And then Scheme decides to garbage collect. It needs to know that there's a pointer to that particular closure that's existing over in the Python world.
But on the Python side, who is pointing to this closure? So if you wrote your code in such a way that you are actually stashing a pointer to this instance in a Python global variable, then you won't be able to garbage collect that. But if it's only accessible through
wait, how does the Scheme garbage collector know that this pointer exists over from the Python heap into the Scheme data, to keep it from being collected?
It's so from what I remember, we use a Gambit specific structure that we know won't be garbage collected. If I'm not mistaken, it's the RC, Gambit CFI RC code.
On the Python side, there's a reference counting. So the Python objects are reference counted. So if Scheme has a pointer to a Python object, the reference count will be bumped by 1 because there is a reference from Scheme to Python. So that means it won't get garbage collected as long as Scheme holds on to that object, well, from the scheme side. And we have a finalizer such that when that reference is lost from the scheme side, basically the reference count goes down. So if even Python didn't have a reference to that, then finally the object is garbage collected on the Python side.
All right. Well, thank you very much. Let's thank our speakers, and we'll move on to the next talk.
Thank you.
Thank you.
Okay, thank you.